Okay, good afternoon, everyone. We have Alejandro Morales today, speaking from UMass Amherst, the other side of the country, but Alejandro actually was a postdoc at UCLA for 3 years, so he's sort of local and familiar to us, and he will be telling us about the Okounkov-Olshanski formula for standard tableau of skew shapes. Go for it.
Thank you very much, Greta. Thank you all for coming. Thank you for the invitation. It's great to be back, so to speak, in LA and talk about a subject that actually I got interested while I was a postdoc at UCLA with Igor Pak. So it's good to talk about this. Please stop me at any time. So this is joint work with Daniel Zhu, who is a second year undergrad student at MIT. And it was done with this MIT Primes program. Okay, so and pretty much the focus is really what's happening here. So we'll kind of spend the time explaining this as we go along. Okay. So just to get some notation right. So a Young diagram, we denote it in English notation 432. And the skew shape, you denote it, you kind of bite off 2, 1 out of a skew shape. I think that it's possible that even in the USC math department, some people do English notation and others French notation, but we're going to stick with English notation. Yeah. Okay, and so a standard tableau is which is basically what we're going to talk about today, is a filling of the Young diagram with, if you have n boxes with the numbers 1 up to n, increasing in rows and columns. So this is an example of a standard tableau here. And there's actually, for this shape 3, 2, there's 4 more. Okay. Okay. So then we're interested in the number of such tableau. So here the number would be 5. Okay. And we're also going to be interested in the number of standard tableau of skew shapes. So when you bite off mu from lambda, and we also, if you have n boxes, we fill with the numbers 1 up to n, so you're increasing in rows and columns. So this skew shape, kind of like, just because you bit off 1 box, it's pretty much the same as the example before. So here we would say that the number of standard tableau of shape 3, 2, 1 is equal to 5. Okay. And why do we want to compute these numbers? Maybe there's several reasons. Let me give you a few. So first is that these numbers of standard tableau count linear extension of certain posets. So these posets are obtained kind of from the cells of the Young diagram. So for example, here, for the first example, here is the associated poset. So, and somehow you remember that this was kind of where the smallest entry would go. So this is the minimal element. So this is the Hasse diagram of the poset. Okay. And in a skew shape, you do the same. So for example, here in the skew shape, you get the zigzag. Okay. So, and if you care about linear extensions, then this is a good example of a good model, and nice things happen, which doesn't always happen when you count linear extensions. And special cases include, of standard tableau, include binomial coefficients. When you have a shape that's a hook, when the shape is just 2 rows, the number of standard tableau is given by the Catalan numbers. Okay. And even when you have skew shapes like zigzags, where you have a connected shape that's a zigzag, so you have no 2 by 2 boxes, the number of standard tableau of that zigzag is equivalent to counting permutations with a given descent set. Because if you want to be increasing in rows and columns, like the reading word, like if you fill a standard tableau, if you read it like this, you're going to be increasing here, decrease here, increase, decrease. So you're really telling the permutation where the descents are. Okay. And counting permutations with descents is important in enumerative and algebraic combinatorics. And so these are maybe enumerative reasons of why we care about these numbers. And it's also of interest in algebraic combinatorics. So the number of standard tableaux of a straight shape gives the dimensions of irreducible representations of the symmetric group. And you might have seen this formula in a course in algebraic combinatorics. And for skew shapes, the number of standard tableaux give dimensions of certain irreducible representations of Hecke algebras. Okay, so maybe a reason we care about this in algebraic combinatorics is they give you dimensions of spaces. Okay, so let's remember I mentioned hooks were counted by the binomial coefficients because there's a 1 has to go here and this has to be increasing. So once you pick, so there's kind of 8 boxes left here. Once you pick what goes here, there's only one way to pick put the entries. So that's just choosing a subset. Okay, and in general you get any binomial coefficient. So so it's not a coincidence you get a nice formula for straight shapes. For all straight shapes, and there is this the famous hook length formula of Frame, Robinson, and Thrall that says that the number of standard tableaux equals the number of boxes factorial, and you divide by these numbers called hook lengths. So for a cell ij, the hook length is the number of boxes on this hook. Okay, and I'm going to give you lots of formulas. So I have this like maybe thing going on here that this is like just yeah, I guess in LA you have this like Hollywood culture. So maybe we're going to compare like these like universes of superhero formulas. So this is the hook length formula, really from 1954, and it's just a wonderful formula. So let's do an example. So here is the shape 2, 2. So the hook lengths are 1, 2, 2, 3, because they're the lengths of this, 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 and this. So you take the number of boxes factorial and you divide by these numbers. Okay, and the answer is 2, which is the number of standard tableaux. Okay, so really a wonderful formula. Here is the example I just did. And there's probabilistic proofs lots of proofs, but let me highlight 2 proofs. The probabilistic proof by Green, Nijenhuis, and Wilf from 79, and the bijective proof by Novelli, Pak, Stoyanovsky in 97. Okay, so here is the hook length formula. What happens for the number of standard tableaux of skew shape? Are there any questions to here? Okay. Well, one example of a skew shape is a reverse hook, because you take a rectangle and you remove a smaller rectangle. But this is by kind of rotating or symmetry. It's the same as counting the number of standard tableaux of a hook shape. So it's also given by a binomial. Okay, so reverse. So let's call this a reverse hook. It's also nice. So that's encouraging. Let's look at another family of skew shapes. These are zigzags. Okay. So the number of standard tableaux are given by these numbers, and before f lambda divided the n factorial, so you wouldn't see primes bigger than the number of boxes. But here you have 6 boxes, and you have a huge prime. So something more interesting is happening here. So there's no product formula known, and we'll see that. But the numbers you get are still interesting. This sequence 2, 5, 16, 61, 272 are called the Euler numbers, and they count alternating permutations, so permutations that go up and down. Okay, and these numbers, for example, still have beautiful combinatorics. One little property of them. Let me mention 2 properties. If you put them in a generating series, you get secant plus tangent, and maybe also if you maybe a more connection to analysis is that up to a sign they're equal to a Bernoulli number, and up to a sign and a constant and a nice factor they're equal to a Bernoulli number. Okay. Okay, so even though there's no product formula, no product formula known, there still is some very nice formulas. So this is a determinant formula that you obtain from the Jacobi-Schrödinger formula of Schur functions, and this is something I learned kind of, and I got kind of learned as being a postdoc in LA. In LA was like, oh, determinants are really fantastic, they're really powerful. So I thought this superhero was appropriate. Even though there's no product formula, you can still compute them quite fast. So here is an example of, for this zigzag here, of 4 boxes. It's not so important how to remember the formula, but you get a 2x2 determinant, and the formula is, and you get 5. Okay, so you could get 61 as a 3x3 determinant, for example. Okay, so that's still pretty good, but it's a determinant, so it's alternating. So we could be a bit picky and say, well, are there positive formulas? Are there any questions? So we could be a bit picky and see, well, is there, yeah, so is there a positive formula? So, sorry, let me try to see my screen too. Okay. Please let me know if you have any questions or you have to monitor the chat. So, so there is a positive formula, kind of pretty old one. Using the Littlewood-Richardson coefficients. So you can write the number of skew standard tableaux as a positive sum of the number of standard Young tableaux that have of straight shape that have the hook length formula. And then you multiply by these non-negative coefficients called the Littlewood-Richardson coefficients. So here's an instance of that. So this thing before that we computed with the determinant is the sum of these two number of standard Young tableau, and these coefficients, these green coefficients here happen to be 1, and you get 5. Okay, but then you have to kind of use your favorite rule to compute these little Richardson coefficients, and you would be good to go. But then computing these numbers is computationally hard, so you could be a bit more picky and say, well, is there maybe something newer than this? Okay, and maybe you start seeing kind of how I'm dividing this cinematic universe of superheroes. Okay, so for example, you could say, well, the number of terms of this formula is kind of summing. If you fix lambda mu and you sum over all nu of these coefficients, and this counts something, but it's not. This counts something, but it's not entirely nice. Counts the number of standard Young tableau of shape lambda mu, whose reading words are involutions. But that's pretty tricky to count. So okay, so let's move way forward to the 2014. Naruse announced this positive formula that I want to tell you about. I'll tell you one more formula, but this is the second last, okay? So I'll explain what it is, but it's maybe you have a factorial, you're summing over hooks, products of hooks, and you're summing over something, and these something are excited diagrams. That if you've seen talk about this, probably know what they are, or Sui Hong, he gave a talk earlier in the semester at UCLA, the UCLA seminar about this. So kind of with Igor and Greta, we started kind of the study of the combinatorics of this formula, and it's been lots of applications. For example, Sui Hong has used this formula with Greta and Igor and others, and so it's been kind of had some applications. So here we've written 3 papers about them, and we have to write another one. So there might be So let me explain what this is. Okay, so an excited diagram is the following. You have a subset of the cells of lambda, and we say that an element in S is excited if the element, so the blue element is excited if the element right to the right below, and diagonally are all empty. Okay, and it's still in lambda. And an excited move is replacing that cell by the cell diagonally below. Okay, so this looks better. Maybe it doesn't look so good like this, but so the cell kind of slides down. Okay, that's an excited move. Okay, and then so here's again what an excited move is. So an excited diagrams are diagrams that you obtain from mu by applying excited moves on excited cells. So let's look at an example. Here is for 2 to 1. There's only 2 excited diagrams. You start with mu and then you do as many times as you can, you move down. So here, if we have a reverse hook that's a bit bigger, you can slide this down, which then kind of frees these 2. So either this moves down or the one on the top moves down. And then this liberates this one. And if it moves down, you get this excited diagram, which is the same as you would obtain if you slide this one, but so you don't count it twice. And then this one can go down, so you get, so in total you get 6 excited diagrams. Okay, and the number of excited diagrams of a reverse hook is given by this binomial coefficient. Okay, and you can see that the complements are lattice paths. So you can see why the answer is a binomial coefficient. If you look at the zigzags, the ones that give you these Euler numbers, the number of excited diagrams are just dig paths. The complements are dig paths. So the number of excited diagrams here is given by the Catalan numbers. Okay, so that's nice. And if you take a thick zigzag, so so from now on, when you see delta n, and I didn't define this, sorry about that, delta n is just a staircase. Okay. Okay. So now we're going to consider thick staircases. Okay. You take a triangle and remove another triangle from it. Here's an example of an excited diagram. And if you look at kind of the complement, the excited diagrams in red here, the excited diagrams are they're in bijection with tuples of non-crossing dig paths. So in this case, the number of excited diagrams for a thick zigzag is a determinant of Catalan numbers. Okay, and this is and there's so just some cases where the number of excited diagrams is nice. And in general, for all skew shapes, the number of excited diagrams. Sorry. Yeah, go ahead. Yes.
Sorry, but I have a question about the previous diagram. So you mean that the gray part is removed?
Yeah, because when you slide down, yeah, that's a good question. So when you slide down, like this only slides down here, slides down here, slides down here. So this is just not interacting. This is might as well. So that's why it's in gray. Everything kind of happens. All the action happens here.
Got it.
Yeah. Yeah. Sorry, I shouldn't explain. I wanted to highlight the dig paths to the side. And for all shapes, there is a determinant formula for the number of excited diagrams. Okay, and it's not so important to see what the details are, but there's a determinant formula for the number of terms. Okay. Okay, so now maybe let's go back to the formula of Naruse. So now we know what the excited diagrams are. So you take the n factorial, you sum over excited diagrams, and you multiply hook lengths. Okay, so it's kind of easy to remember. You more or less. I mean, you have to remember what the excited diagrams are, and then you sum over the products of the hook lengths of the complement. So here we have 1 to 1, and here we have 2, 3, 2. And you sum this, you multiply by n factorial, and you get the number of standard tableaux. Okay. Any questions about the Naruse formula? So it's very satisfying in the sense that it looks very similar to the hook length formula, and you have this nice excited diagram model to remember it. Okay. So I think we were working on this formula with Greta and Igor, and I think maybe Per Alexanderson mentioned that he had seen another formula that was studied by Stanley, so kind of before the Naruse formula there was another positive formula. So let's call it the original positive formula for F lambda mu.
I have a question regarding the last slide. Yeah, so 3 factorial is not the multiple of 12. So this Naruse formula actually doesn't give you, in some sense, a combinatorial
Yes, absolutely. So the pieces are not integers, and they add up to 2. If you scale them by lambda factorial, they are integers, but not by lambda mu factorial. And there is no, we have several proofs with Greta and Igor of this formula. There's also a proof by Matias Konvalinka, but there's nothing as nice as the probabilistic proof or the bijective proof of Pak-Stoyanovsky. So that's kind of missing somehow. Yeah. Does that answer? Yeah. Okay, but kind of before, in the late 90s, there was this other formula, and that's kind of the focus of today. We got to it finally. Is this Okounkov-Olshanski formula. So maybe it has some similar ingredients. You have the number of boxes factorial. You divide by the hook lengths of all of lambda, and you sum over semi-standard Young tableau of shape mu, and you have this product that's kind of, I always have to look it up somehow. I cannot remember it. Okay. So this is kind of, if kind of Naruse was like the Iron Man, this kind of came before, is the original Avenger. It was the Captain America of formulas. Okay. So let's do an example. Okay, so you sum over semi-standard tableau of shape mu. So in this case, mu is 1, and the entries are less than or equal the length of lambda. So this has length 2. So there's only 2 possibilities. Okay. And then there's some weight. So don't worry too much about the weight, but here is what it is. Okay. And you take n factorial over the hook lengths and you get the number 5. Okay. But please don't worry about this. We'll understand it in a better way. Okay. And out comes the formula. Okay. If I take the transpose of the shape, now my D changes. So now the D is 3 instead of 2. So if you take the transpose, the number of tableaux don't change, the number of standard tableaux don't change, but the formula is different. So this doesn't happen with Naruse. The Naruse is invariant under this, under taking transposes. Okay, so it's a bit more subtle, or yeah, it has some differences, I guess. Okay. Any questions? Okay. But even when you read it, I mean, at first look, you have this minus I, so you might think, well, maybe some terms might vanish or be negative. So for example, here, for this shape, in this case, what's D? Can you tell me what D is? Someone in the audience or in the chat? Oh, there's some question in the chat. Oh, thank you, good. Yeah. So here D would be 3. So you could put numbers 1 up to 3 on this tableau of shape 1, 1 of shape 2, sorry. And if you take the shape 3, 3, the semi-standard tableau 3, 3, just believe me that you get a 0 weight. Okay. So somehow the sum here is not completely tight. Some of these terms are 0, maybe some are negative. Okay. Okay. Okay, good. So kind of let's put these two formulas one next to each other, and let's try to compare them. Any questions?
Alejandro, so I get confused by what you say at the last. You say that this formula can be negative.
Well, I mean, just kind of it cannot be, but a priori it's not clear. Like as written, it's not clear, but it is non-negative. So yeah, it is non-negative.
Okay.
It's not clear, not completely clear. Not too hard to see, but not too clear. But already you're summing over terms that could be 0, like this example. Okay.
I see. Okay.
So one of the things we're going to do is we're just going to focus on the non-negative, on the positive terms. Okay.
Just one more question, but can you get Naruse from this or the other way around? Like, what is the relation between this and the Naruse?
Yeah, good. I have something at the end of the talk, so maybe if you ask me at the end, I'll explain the relation. I mean, now I'm going to relate them, but then I'm going to explain an algebraic. I can explain an algebraic relation, but I have it after the thank you. Okay. Okay. Okay, so I've told you about Naruse formula, excited diagrams. There's a determinant formula for the number of terms. Some special cases for the zigzag. We got there's Catalan many terms. And for the thick zigzag, we get a determinant of Catalan. Okay. So let's try to compare this here on the for the Okounkov-Olshanski. Okay. So first, the first thing we're going to do is we're going to give a maybe more Naruse type reformulation of the Okounkov-Olshanski formula. Okay, so this one is in terms of reverse excited diagrams. So if you remember, an excited move was sliding a box down. Okay, so reverse excited diagram is the opposite, kind of moving up. Okay, so this moving up. Okay, and there is this line here that I'll explain in a second. So, but focus now on the blue cell. It just moved back. Okay, so we need to view the skew shape as a shifted skew diagram. I'll explain that in a second. And we're going to draw diagonals at the end of each column of mu. And then a reverse excited diagram, and this is the set, are diagrams obtained from the skew shape by doing reverse excited moves. Okay, so let's so maybe let's do an example. Okay, so here is my skew shape. Okay, so when I make it shifted, it just means that I'm going to attach to it a staircase on the left. Okay, so I'm making a shifted shape. Okay, so it just means like stick a staircase here. Okay, that's to make it shifted. Okay, and now we're going to do reverse excited moves on. So instead of for Naruse it was on mu, for Okounkov-Olshanski is on the skew shape on lambda mu. Okay, so sorry, can you tell me? Yes.
Sorry, question. But how big is? Why is it that you test a 2 staircase rather than a 3 staircase?
Yeah, I guess yeah, you're right. So I guess there is this situation which is going to happen already, that if I have something in the diagonal, then that can kind of move back. So that explains why. I mean that. So it wouldn't matter if we add one more. I guess I'm adding kind of the things where the interaction is going to happen. But in general, yeah, you're right. In general, I have lambda, and I just attach to it a staircase of that size. Okay.
Okay, I see.
Okay, so what are the reverse excited moves? So what are the reverse excited diagrams? So what is the only? Can you tell me what is the only thing that can move here at the moment? So this one is trapped. This one is trapped, but this one is okay, right? Okay, so so this stays put, and this one can move. Yeah. And that liberates this one. So now we have, sorry, this stays there, and that's it. Okay, so what happened is that this moved here. Okay. And now I have to tell you what's happening with these red lines. So the red lines just, I'll explain the red lines, how do you draw them to begin with, but the rule is that whenever you do an excited move, the red lines move down. Okay, so this just moved down, so this just moved down, and now this is going to move here. Okay, but that's not so, that'll be important for the weights. But okay, so is it clear what a reverse excited diagram is? Okay, so a bigger shape would be if you have this kind of zigzag, you attach the staircase here, okay? And these red lines is that for each, at the end of each column of mu, you draw a line like this, okay? And then you just let them interact with your excited moves. So when this moves here, this line moves down, okay? Okay, any questions what the reverse excited diagram is? Okay, so here is Okounkov-Olshanski. The way I now remember it, so it's a reformulation, is that you take the number of boxes factorial divided by the hook lengths, you sum over reverse excited diagrams, and then for each excited diagram, so these lines are called, these red lines are called diagonals. You take the arm of that, the arm length of that cell. Okay, So let's look. So here are the 3 diagrams from before. So let's do it now. So how many boxes do we have in lambda mu? N equals. Can you put it in the chat, someone? How many boxes here? 4. Thank you. So we have 4 factorial. We divide over all the hook lengths of lambda. So the hook lengths are 1, 1, 2, 3, 4. Okay. Okay, and now the weights. So I look at the red lines and I say, what is my arm length? So my arm length there is 2. My arm length here is 2. And my arm length here is 1. Okay. And that's the rule.
Sorry, I guess I get confused, Alejandro. So I don't get what is how do you get the number in the arm again? Why is it as 2, 2, 1?
Yeah, so you start, you go to these red lines, and you just calculate the arm length. So here it's 2.
Ah,
here
only the horizontal. I see.
Only for those red lines, yes.
I got it.
So 2, 2, 1. Okay.
Wait, I see. Wait, so then I guess that this formula will change if you actually transpose the graph now. I mean transpose the picture.
Yes, exactly. Yeah, yeah, and that's why. Yeah, and yeah. So that shows a difference. Yeah, there's a question.
So, wait, I have one question. So
yes.
Are you gonna have as many red lines as there were boxes in the original mu?
Yes. So the number. Yeah, exactly. Yeah, it's a good point. Okay. Yeah. So the number of diagonals is the size of mu. Yeah. So because here we have 3, 2, 1 like this, exactly the size of, and they're just moving down. Okay. Yeah. So yeah, that's a good point. Yeah. Okay, so that's a reformulation of Okounkov-Olshanski using reverse excited diagrams. So after studying the Naruse formula for so long, I'm a bit biased. So when I see this reformulation, I prefer it. But maybe you prefer the other one, the original one. So that's okay. So how do you go from one formula to the other? Okay, so here is the original Okounkov-Olshanski formula. And kind of answering Greta's question, there is mu many a product of size mu here. So, okay, so let's kind of restrict. So, well, the original terms of the formula are indexed by a semi-standard tableau of shape mu with entries less than or equal d. And now if we want this to be positive, I just need that this size of lambda is bigger than I minus j. Just by I want to force that that's positive. Okay. So I'm going to call tableaux like that. I'm going to call them Okounkov-Olshanski tableau. So they're of shape mu. I want to make sure that all of this is positive. Okay. So this will be excluded here because this box here does not satisfy what we want. So let's just check. So d here is 3. So we have lambda of 3 plus 1 minus the value of the tableau, which is 3. And the content here is minus 1. Well, minus the content is minus 1. So, oh, sorry, I think that's the subscript. And then I have minus 1. Okay. So this is lambda 1. Oh. No, this should be lambda 3. Okay. Okay, I must. Okay, maybe I think I did something wrong here.
Sorry, is J the row index or the column index?
It should be the column, yeah. So
shouldn't it be plus 1?
Oh yeah, plus 1, yeah. So thank you, Brendan. So let's see if I get this right. Let me see the. Oh, I should use this inequality. So the content here is 1, and let's see if this is less than lambda 4 minus the value of the tableau, and that's lambda 1, which is 3, so that's okay. And let's check the other one. 0 less than or equal, and I have lambda 4 minus 3. Which is also true. So wait, wait, what am I doing wrong here? Wait, this term is not supposed to be here. Okay, maybe, sorry, I think, I'm sorry, this, sorry, sorry, I think the tableau that's excluded is 1, 1, because if you do, yeah?
Yeah, so there is a question in the chat, what is TIJ? And TIJ is exactly the entry.
Yeah, this is T, thanks, sorry. Yeah, this is T, so I think I'm doing a mistake here, but this is, okay, I should have, this is lambda 1, and this is, no, lambda 3, and this is 1. No, but this is all satisfied, okay.
But should the inequality be strict? Is that the issue?
Oh yeah, I want it to be strict. Yes, you're right. Because I want it to be, yeah. Thanks. Yeah. Sorry. Yeah, I want to make sure this is positive. So the problem is here I have an equality. Thank you, Brendan. Sorry. Okay, so this is no good. Thanks. Sorry about that. Yeah. Okay. I think I botched this up, but I need to have this restriction. But you see, it's kind of tricky to get it right. Okay. So that's okay. Sorry about this. I should have been 1, 1, and this should have been strict. Okay, and it's violated because I have an equality here. Okay, thank you. Okay, okay, and the first thing is that these Okounkov-Olshanski, like on the picture from the beginning, the Okounkov-Olshanski tableau are in bijection with certain lozenge stylings. So here's a tableau for the shape. So this is lambda mu is just a zigzag. Here is one of the tableaus that satisfies those restrictions I messed up. So if you translate, if you kind of translate your tableau into lattice paths, the usual way you would see on enumerative combinatorics. So the first row here is going to the heights here, 1, 2, 3. This is going to heights 2 and 5. And this is going to this is going to height 5. Okay, if you translate this into paths the usual way, then you can then translate these paths into the red paths. So this should have been red, but these red paths here correspond to these paths here. Okay, so I claim that all these red paths here correspond to these red paths here. Okay, and once you have these red paths, they define a lozenge styling of this region. Okay, so maybe yeah, so you get a bijection from these tableaus to a certain lozenge styling, which when you filled it up is if you had this and you forgot about all the green, red, and blue paths. So you get a lozenge styling of that region. Okay. So and this is kind of this is going to be the master object. From here, we're going to go to different places. Okay. And so maybe, I mean, for now, maybe just hopefully this step is clear, and then I claim that these paths here uniquely give you a lozenge styling of this region, and you should just look at these paths. These paths here should be the red paths here. Okay. Okay, so that's the first. So you go from these tableaus here of shape mu to certain lozenge stylings. Okay. Now we're going to go from lozenge stylings to something called skew flag tableau. So let ft lambda mu to be semi-standard tableau of skew shape lambda mu, where the entry in row I is at most I. Okay, so Okay, and then the next lemma is that Lawson stylings of that same region are in bijection with this flag tableau. Okay, so here maybe let's focus on this just to give an example of this tableau. So here we have, so here again the shape is it was 5, 4, 3, 2, 1, 3, 2, 1, and then the things in row 1 have to be less than 1. The things in row 2 have to be less than 2. Row 3 have to be less than 3, and so on. Okay. And then the Lawson stylings that we had from before are in bijection with that. And to see that, now that's why there's all these colors. So before we were focusing on these red paths. So now to see the tableau, we have to look at the blue paths. So if you look at the blue paths, they're going to encode, by looking at the same at the heights, you're going to encode this tableau here. Okay. So putting everything together, the original tableau of shape mu, with the condition that it was hard to remember that I minus j was strictly bigger than lambda d plus 1 minus tij, they're going to be in bijection with this set of flag tableaux that are much easier to remember, at least. Skew shape with the row I at most I. Okay, and so any questions maybe just of the intuition? So you get to this Lawson styling that has 3 paths, and you interpret one path for something and the other paths for the other thing. Okay. Okay, so let's move on to get to the excited diagrams, the reverse excited diagrams. Here is a definition of the flag tableau again, and just from the thing before, we had that Okounkov-Olshanski tableau are in bijection with these flag tableau. Okay, so finally, flag tableau of skew shape are in natural correspondence with reverse excited diagrams. So let me give you an example. So here's a flag tableau. So to get the reverse excited diagram, the only thing you do is so in some sense a flag tableau is like a lazy reverse excited diagram. So all you need, so these numbers are just telling you they're telling you how far you moved. So let me give you an example. So the smallest possible flag tableau in your class would be where this would be your smallest possible, like where if everything in row I is exactly I, you would get something like this. So then when you're changing, for example, this 2 changed into a 1 here, that means you had a reverse excited move. So the cells are just keeping track of how much you've moved. Okay. So the fact that this is a 1 here is just telling you that this moved here. Yeah. So a flag tableau is like a lazy reverse excited diagram. It's just instead of moving backwards, it's just, oh, I just moved, just recording where you moved. Okay, another example. Originally this would be 4, 5, but if they're 2, 3, it's because this thing moved all the way here. Okay. So it's just telling you how much you've moved. Okay?
Alejandro,
Yes?
sorry to interrupt, but I just have one question. So correct me if I'm wrong, but with the Naruse formula, the number of excited diagrams, not the reverse one, is also enumerated by the flag tableau.
Yeah, absolutely. Yeah, absolutely.
So does that mean that they are one-to-one correspondence then now?
No, so I guess so in Naruse, maybe let me go to the next slide, but yeah, so to explain that. So
okay.
So in Naruse, they're of shape, they're flag tableau of shape. There is this weird thing. So sorry. So Naruse, the excited diagrams are flag tableau of shape mu. In Okounkov-Olshanski, they're flag tableau of shape lambda mu. So you see, it's a different shape and different flags. Okay. Okay, so now putting everything together, the terms in the original formula are in bijection with reverse excited diagrams. So you can reformulate the formula. Okay. Any questions?
Yeah, so sorry, how did you get rid of the negative terms in the Olshanski-Okounkov formula?
Oh yeah, good question, Jason. So we kind of cheated in the sense. I mean, first of all, yeah, okay, sorry, I didn't say that, but there are no negative terms. There are in the original formulation, all the terms are non-negative.
Oh, okay.
Because if you can kind of show, and I think like it's an idea of Greta that if you had a negative entry, you need to have a zero entry somewhere else. So it's kind of like a kind of intermediate value theorem.
Okay.
So everything is non-negative, and we just remove the zero terms, and now we're focusing on the positive terms.
Okay.
And these are exactly these, yeah. So yeah. Sorry, I didn't mention that, but yeah, the formula is non-negative.
Oh, thanks.
It's not apparent from the beginning from looking at it, but it is. Okay, so I've told you about this. So how about the number of terms? So remember the number of excited diagrams of the Naruse formula. So in Naruse, it's given by a determinant. Okay. So now with Daniel, we showed that for Okounkov-Olshanski terms, the positive terms, not the zero, not the, because if you include the zeros, there's a product formula for them, the Stanley content formula, but the positive ones, so the positive terms, so the number of positive terms has also a determinant formula, and there's two of them. Okay. Okay, so very similar to maybe Sui Hong's question, very similar to excited diagrams. Okay, the proof comes from the same place actually, and it's just that there's a determinant formula to count flag tableaux. So this is the number of flag tableaux. So as a result of Michel-Wax and using or you can see it using the Kessel-Vienno theorem, if you count the number of semi-standard tableaux, so what are these? These are semi-standard Young tableau of shape lambda mu, where rho I, the entries are less than AI and bigger than or equal BI, there is this general formula, determinant formula. So, and this kind of proves that both actually. So for Naruse, the shape is mu and there's no BIs. I mean, you don't care about that. And the AIs are something that we didn't talk about today. For Okounkov-Olshanski, the shape is skew. There are no BIs. And the AI is just I. Okay. And then you plug the formula and you get both. So using this kind of formula, you get both this one and our formula. Okay. Any questions? Okay, so now let's finish with some special cases. So this is maybe the less technical, well, a little bit more technical at the end, but we're almost done. So can you remind me what were the number of terms for the zigzag in the Naruse formula? Do you remember? Long time ago, yeah. So the number of terms here is a Catalan number. And for this thick zigzag, we had these like non-crossing dig paths. So here we got a determinant. Nope. Here we got a determinant of Catalan. Okay. So let's see what happens in those special cases for Okounkov-Olshanski. Okay, just to finish. So some enumerative combinatorics. Okay, so I need to define one more thing: the Genocchi numbers. Has anyone heard of the Genocchi numbers? Can you raise your hand if you have? Maybe heard of something? Okay, but they're not as well known as the Euler or the Catalan numbers. Good. So the Genocchi numbers are defined like this. So you can see them as up to a sign and a power and a factor. It's a Bernoulli number times a factor. Okay. Here is the sequence from the OIS. So maybe a good, if you want to take a little break, can you tell me what is the handle for this? Can you search these numbers and tell me what is the OIS? You can put it on the chat. What did you get? Hopefully you get a hit. Otherwise, I made a typo. Yeah, thank you, Kai. Remember Catalan. So yeah, what is the OAS for this? The OAS address? Someone?
I get 367, but I guess it's for Bernoulli.
Oh, okay. Okay, let me maybe. Yeah, I think. So I think yes. So hopefully Sunita is right. So this is hopefully this. Okay, but let's see what they count. So they count something. I don't like the name too much, but that's what it is. It's called alternating pistols of length 2n minus 1. So this is a tuple of integers. So these are non-negative integers. There's a better way to say this. So they are in n. Okay, where AK is less than or equal k plus 1 over 2, and AK is bigger than or equal AK plus 1 if k is odd, and AK is less than AK plus 1 if k is even. Don't worry too much about this interpretation, but this is what they count. Okay. Okay, and maybe we've seen Bernoulli numbers before, because I said that Euler numbers were also equal to Bernoulli numbers times a factor. So Euler numbers are proportional to these Genocchi numbers. Okay, so maybe that's a nice relation. Okay, so here's a definition of the Genocchi numbers. So this was conjectured by Igor, Greta, and myself. So and we prove it here that the number of Okounkov-Olshanski terms of the zigzag, so this is the zigzag, equals a Genocchi number. Okay, and here is the proof. So remember that Okounkov-Olshanski counts reverse excited diagrams, which equals flagged tableau of skew shape. So they count semi-standard tableau of zigzag shape with entries in row I at most I. And the reading words of those things are exactly what you're looking for. So that's it. The reading words of that is exactly what you want. So if you read one of these things, if you do the reading word, that's exactly going to be an alternating pistol. So it's it's the same interpretation. Okay, so for the zigzag we get Genocchi numbers. Let's see what you get for thick zigzag. So remember, this is a thick zigzag. Okay, well, maybe more like this. Okay, so the number of Okounkov-Olshanski terms. So remember, for Naruse it was a determinant of Catalan. Here we get a determinant of Genocchi numbers scaled by a factorial times a factor. Okay, so similar, kind of like you replace Catalan by Genocchi and you have to add a factor. Okay. Okay, so this generalizes the previous case when k equals 1. When you plug in k equals 1, out pops one Genocchi number. But this proof is much harder. So we need to use a symmetric function called McDonald's ninth variation symmetric function, and the definition is here, but kind of running out of time. But you have a function that's where your variables are indexed by a content. So this is a content which I have not defined. Okay, and these functions, if you do an evaluation of the parameters in ones and zeros, out comes the number of terms. So up with an evaluation, you can get the number of positive terms of Okounkov-Olshanski. And these functions satisfy a generalization of the Jacobi-Trudy identity called the Lascaux-Pragat's identity, or a variant. And this was proved actually just last year by Angel Foley and Ron King. So that gives a way to compute these functions as determinants of functions of the same kind of functions, but of simpler shapes of zigzags. And then out comes this result. Okay, so this is much more technical. So a better proof of this would be great. And just to finish, this has a surprising relation. So maybe if you can just wake up here for some numerology. So remember that Euler numbers, which discount the number of standard tableaux of a staircase. Okay, and this count the number of Okounkov-Olshanski terms of the same shape. Okay, so something really surprising happens that here in this thing you see, because they're both multiples of Bernoulli numbers, you get that the number of standard tableau of that shape, of zigzag shape, is proportional to the number of Okounkov-Olshanski terms of that shape. This doesn't happen with Naruse because you get Catalan and Euler, and Catalan and Euler are related, but they're not proportional to each other. But here they are. And this holds for all thick zigzags. So you get this funny identity that the number of standard tableau of a thick zigzag is proportional to the number of Okounkov-Olshanski terms. So this is kind of a surprising corollary, and it has some asymptotic applications. So at some point we with Greta and Igor, we were interested in the asymptotics of this sequence. So this is the logarithm of the number of standard Young tableau, and you have to divide by 1/2 n log n, subtract and so on. Anyways, we're interested in this, and this corollary gave us some allowed us to improve the upper bound for what this value is supposed to be. But this we had the best upper bound for like 2 months, because then Igor found a better upper bound. But it also shows that the asymptotics of this, the number of standard Young tableau of this shape, is the same as the number of the asymptotics of the number of terms. So okay, so I'll finish with that. Thank you.
Thank you very much. Any questions before I stop the recording?
Yeah, so you started with this Okounkov-Olshanski formula, and you sort of eliminated some terms that were 0. That's kind of
yes, correct.
I guess. And do you have a sense of like how many terms that was? Like how much more efficient did the formula get?
Yeah, I guess we have not done that, but so the total number of terms is this. The number of semi-standard tableau with entries less than or equal this, and this has a product formula, the hook content formula.
Yeah.
So maybe yeah. Anyways, yeah. I have so for example, for the zigzag, you're comparing semi-standard. I think in this case I've computed the ratio, but I don't know what it goes to. So I guess, so I mean, this should be doable. We didn't address it, but it's a good question. Yeah. I think at least for this example, maybe the denominator here is a known sequence, but yeah, mm-hmm. but I don't know what it is as n goes to infinity. I don't know.
Okay.
Yeah, it's a good question. I think not. My intuition is that not many vanish, but no, that's not quite true. So let me go back. So yeah, actually, I can say a little bit more. So you know how here I said we can improve the lower bound, we improve the upper bound on this. That upper bound is improved by using the fact that this is less than or equal semi-standard Young tableau of shape mu with entries less than 2k. So there is still a big gap because this upper bound was not so tight. I mean, it's better than what it used to be, but yeah. So sorry, just to answer your question, that is exactly one way of using this to get bounds, because this has a product formula.
Yeah, I see what you mean.
Okay, so maybe I can give you some numerology. Just give me a second. I'll look it up. Well, if there's another question, let me tell you the numerology for that shape.
Other questions?